Okay, we will get started. We're doing 8-5 today and on Wednesday, but it's gonna kind of be chalked up because the way that the questions are ordered doesn't necessarily go with how I feel like they should be. So I'm going to do them how I want. It's not gonna be that big of a change. We're just gonna leave out number 3 and we're gonna do it on Wednesday after we do some of these other problems. Okay, now 8.5 is talking about rational functions, and rational functions are functions that have a numerator and a denominator. The first kind of problems that we're going to talk about is the domain of rational functions. This is what we started with on Friday. Remember how we were given a function and it had a numerator and a denominator, and we were asked to find what makes the denominator, what makes this fraction or this rational expression undefined, and that had to do with the denominator equaling 0, right? That's what you want to avoid because you can't divide by 0, it's undefined. So when we're talking about the domain of a rational function, x can be anything except what makes the denominator 0. So looking at a problem like number 1, it says determine the domain of this function. And we have f of x equals x squared over 9 minus x. Okay, so if we're going to find the domain, we need to find out what makes this undefined. So what happens is we need to say, well, 9 minus x cannot equal 0. That's what we want to avoid. So just set it up to not equal 0 and then solve it for x. If I'm solving this for x, that means I need to get the x by itself. But I noticed that this is minus x. So if I add the x, it'll be positive x over here. And it'll be all by itself. So let's see, on this side, I'll have the 9. Bring down my can't equal sign. Over here, all I have is the x. So x cannot equal 9, right? If x is 9, I would have 9 minus 9, which is 0. That's what you want to avoid. So what we want to tell the domain is that x can be anything but 9. Anything on the number line from negative infinity to positive infinity, except the number 9. So I'm going to show that. It's going to ask you to put in the domain and interval notation. So that's what I'm going to show it as. So all the numbers on the number line except 9 would be from negative infinity to 9 in union with 9 to infinity. So that's all the numbers from negative infinity to positive infinity, excluding the number 9. All right, number 2 is the same kind of problem. Also asking for the domain of this rational function. This time our function is f of x equals 3 over x squared plus 2x minus 35. So this time I'm noticing that my denominator is an x squared, which means there's going to be 2 solutions. There's going to be 2 zeros, 2 numbers that would make the denominator equal to 0. That's what the x squared tells me. Okay? Anytime it's x squared and you're trying to solve, right, which is what I'm doing, x squared plus 2x minus 35 cannot equal 0. That's a quad, isn't it? It's x squared, which makes it a quad, which means I can go straight to my quad program and put in the a, b, and c. I'll do that in just a minute. If you don't have the quad program now, now is the time where it's going to start saving you a lot of time. If I don't have it, though, I could factor this. Get my 2 factors, x and x for x squared. Factor factors of negative 35 that add to positive 2. Let's see. 35's factors are 35 and 1, 7 and 5. I'm going to use the 7 and 5 pair, right? Because I'm trying to add to 2. Now, if I'm multiplying to equal negative 35, I need to manipulate my signs, right? I need one positive and one negative. If I'm going to add to positive 2, that means my 7 needs to be the positive and my 5 needs to be the negative. That's how you would get positive 2. So I need a plus 7 minus 5. So here's my factors. I would set them both and say neither one of these things can equal 0 and solve them for the x's. So here if I subtract 7's, I would see that x cannot equal negative 7. And here if I add the 5's to both sides, I would also see that x also cannot equal 5. So there's two numbers, like we said, that would x cannot equal, negative 7 and 5. So also remember, you could have done this in your quad program. So if you went to program and down to quad, so again, your quad program and enter your A, B, and C. Remember, A is the number in front of x squared, so that would be a 1. B is the number in front of your x, which is 2. And C is your constant, which is negative 35. So there's your A, B, and C. When you hit enter, look what you get. 5 and negative 7, which is exactly what I got when I solved it by hand, right? The quad program is just going to do that a lot faster for us. So how am I going to show this in interval notation? I need to show all the numbers on the number line except negative 7 and 5. So I would start off with negative infinity. Now, coming up the number line, if I'm starting at negative infinity, who am I going to run into first, coming from negative infinity? Am I going to run into negative 7 or positive 5? You're going to run into that negative 7 first. So negative infinity to negative 7 would be all the numbers below negative 7. I'll also want to include the numbers between negative 7 and 5 because they're fine. So in union with negative 7 to 5, so that includes all the numbers between negative 7 and 5. And then what's the last group of numbers you need to include? All the numbers above the 5. So from 5 to infinity. So those 3 parentheses, all the numbers below negative 7 are included here. Between negative 7 and 5 are here. And then above 5 in that last one. Okay, number 3 is the problem that we're going to leave out, and we're going to come back to it on Wednesday after we get some more knowledge. Okay, number 4, we're leaving out all the way together, So when you get to number 4, when you're in math lab, it'll just say that your instructor's already given you credit for this problem. It has something in it that we do not cover called an oblique asymptote, and we don't cover that. So I'm omitting number 4. Now, starting with number 5, let's talk about what a vertical asymptote is. Okay, these rational functions do weird things on the graph. They do different things all over the place, okay? There's these lines that can be on a rational function. They're invisible lines. You don't see them. It's kind of like this right here. This is what a vertical asymptote would look like. So there's one there and one there. So they are shown on the paper as like a dashed line. So here's what a rational function would look like, just a made up one. Okay, let me get a. Will look something like this. Here's what a vertical asymptote does. It is where your rational function comes, but it never crosses it. It comes right up and then just starts going right up next to it. It doesn't ever cross through that vertical asymptote. Okay? And they're vertical, these vertical lines. So if you'll notice, this part of the function, it comes right up next to the vertical asymptote, but it doesn't touch it or cross it. Same thing over here. Comes right up to it right here, but doesn't touch it or cross it. So that's what a vertical asymptote is. All vertical lines come in the form this. X equals a number. For instance, this vertical asymptote is at 1, 2, 3, 4. So it's at x equals -5. That would be the equation of that vertical asymptote. X equals -5. This vertical asymptote, since it's at +3, would be x equals 3. So all vertical asymptotes come in the equation form of x equals, and then whatever number it crosses through the x-axis at. So now we're going to find out how to find the vertical asymptotes of the graph. The vertical asymptotes, kind of convenient that it comes right after domain, because vertical asymptotes are also found at zeros of the denominator as long as they are not also zeros of the numerator. So vertical asymptotes are so they're zeros of the denominator as long as those zeros are also zeros of the numerator. So remember how we were just finding the zeros of the denominator by saying, when we were doing the domain, we would set up the denominator and say can't equal 0. Whatever the numbers that we solved x, whatever x ended up being, those were the zeros, right? Well, the numerator, if it has an x in it, it also will have a 0, whatever would make it 0. So the vertical asymptotes, those dashed imaginary lines that the graph doesn't touch, are at the same zeros of the denominator, like the domain, as long as they're not also what makes the numerator 0. So let's look at some of these, like number 5. My function is f of x equals 1 over x minus 4 squared. So I'm going to find the zeros of the denominator and then just check and make sure before I enter my answer that that doesn't also happen to be the zero of the numerator. Okay, I can tell you by looking at this right off is that this numerator isn't going to have any zeros because it doesn't have an x. It doesn't matter what you plug in for x of this function, this numerator is always going to be a 1. And there's no x up there to plug into to change that numerator. So I don't have to worry about there being the same zeros in the top and the bottom. So I'm just going to worry about what makes the denominator 0. It looks like there may be 2 because it's squared, but if I wrote that out and then solve, because that's what x minus 4 squared is, right? It's x minus 4 times itself. So when I solve those, I'm going to get the same answer, right? They're the same factor. So if I solve either one of these, would look like this. Solve it for x, which means I would need to add the 4 to both sides. So x equals 4 is your vertical asymptote. If you graph this, there would be a vertical asymptote right there at x equals 4. Your graph would come right up next to it, but it would never touch it or cross it. That's what you have found, is that there's a vertical asymptote at x equals 4. The next several problems are like this. Let's look at number 6. All right, finding the vertical asymptote. So let's find the zeros of the denominator. I've got x squared, which means there's going to be 2 of them. Okay, not only is there going to be 2 of them, if I wanted to, I could go, since it is x squared, I can take that straight to my quad program, right? If it's an x squared that you're trying to solve, you can always do that in your quad program. If you were doing it by hand, you would have to factor this. So x squared plus 8x equals 0. There's only 2 terms here. So it's not a trinomial. The first thing you're looking for always when you're factoring is anything that the terms have in common, which these both have an x. So it's got a greatest common factor of that x, which means I can pull that out and divide them both by x. Put in parentheses what is left. If I divided x squared by x, it's kind of like I'm taking an x out. So if I take an x out of x squared, then I'm just left with x. Plus, if I took the x out of this term, I would just be left with the 8. So here's my 2 factors that you set equal to 0. So one of them is x, so I'll set it equal to 0. The other one is x plus 8. I'll set it equal to 0. And then solve them for x. This one just happens to already be solved for me, right? X is already by itself. So that's one of the zeros. Here, I need to solve this one, so I need to subtract the 8 from both sides. So that gives me x equals -8. So 0 and -8 are the zeros of the denominator. Now, I do need to double check to make sure that 0 or -8 is not also a 0 of the numerator. With either one of these, if you plug them in here for this x, turn the numerator into 0. No, right? What's the 0 of the numerator? What makes it 0? Well, set it equal to 0 and solve it. So x equals 9. So that's the 0 of the numerator, which is not either one of those. So those are actually the 2 vertical asymptotes. There's a vertical asymptote at 0 and one at x equals 8. Could I have solved this in my quad program since it's x squared? Sure. Remember, if you're using the quad program, you have to know what A, B, and C are. A would be the number in front of x squared, which would have been 1. B is the number in front of x, which would have been 8. Then C is your constant, which is the number over here that doesn't have a letter hooked onto it. Since there is no constant, your C would have been 0. If you plug that into your quad program, it's going to give you those two answers also. All right, number 7, another vertical asymptote. So let's look. F of x equals x minus 3 over 1 minus x. So again, vertical asymptotes occur at zeros of the denominator. So 1 minus x equals 0. I'm going to solve this for x. If I want x by itself, I'm actually just going to add the x to the other side. So over here, I've just got 1 equals x. So x equals 1 is your vertical asymptote, as long as 1 is not also the 0 of the numerator, which it's not, right? 1 does not turn that numerator into a 0. So that is your vertical asymptote, x equals 1. Number 8, same thing. F of x equals 3 over x plus 5, x minus 1. Okay, so it's like it's already done the factoring part of this for me. I am going to have 2 answers because I've got 2 factors. Okay, they're just not foiled together to give me x squared, but it's still going to give me 2 solutions since it's already done the factoring for me. So again, set your factors equal to 0. Solve them for x. So subtract 5's here. So x equals negative 5. Add 1's here. So x equals 1. So just double check yourself and make sure negative 5 and 1 aren't zeros of the numerator. When I look at the numerator, I don't see any x's, which means I don't have to worry about there being any zeros up there. Nothing can turn this 3 into a 0 because it doesn't have an x with it to change it. So it's always going to be 3. So your vertical asymptotes will be at x equals negative 5 and x equals 1. All right, number 9. F of x equals x squared plus 5x minus 14. Over x squared minus 3x minus 10. So the good news about this is this is a quad, right? It's x squared, which means I can find the zeros in my quad program. So let's do that on this one, just to show you how much simpler it is. So if I go to my quad program, looking at your denominator, what is in front of the x squared? A 1. So A is 1, B is -3, and C is -10. So when you hit enter, with your A, B, and C being 1, -3, -10, your zeros are 5 and -2. Now, look at that numerator. I do need to check that because if one of the zeros of the top is a 5 or -2, it'll cancel out that vertical asymptote. It won't be a vertical asymptote if it's the same zero as the top. So again, I just need to go back to my quad program, and this time using the numerator. So this time A is 1, B is 5, and C is -14. So this time, with that A, B, and C, my zeros are 2 and -7. Which are neither one of these, right? So these, since they aren't the same as either one of those are two true vertical asymptotes. So there's vertical asymptotes at x equals 5 and x equals -2. And number 10, this is the last vertical asymptote problem. We have g of x equals x to the third over 3x to the third minus x squared minus 30x. All right, so since this degree of the bottom, which is the degree is the highest exponent, is 3, there's going to be 3 zeros here. It's also not quad right now because it's x cubed and not x squared. So it has to be x squared to solve it using the quad program. But what do you notice about all 3 of these terms? What do they all have? They've all got an x, which means I can pull an x factor out of all of those. So if I pull the x out and put in parentheses what is left, so what am I doing? I'm dividing these all by x. So let's see what's left. If all the terms are losing an x, let's see, this will be 3x squared minus, if I took an x out of here, I'm just left with x, minus, if I took an x out of here, I'm just left with 30. So this is a factor. This is one of the zeros, that x is. But now, look what you have in here. Now you do have a quad because it is x squared. So I can find my other 2 zeros using my quad program, which is what I'll do, right? So I have x squared, I can always go to quad. So let's see, my A would be 3, my B is -1, and my C is -30. We're decimal, so just hit enter again. It'll turn it into your fractions. So 10 thirds and -3. Are the other 2 zeros. Now, remember, you're only a vertical asymptote if you're a 0 of the denominator, but not also a 0 of the numerator. So looking at my numerator, I do see an x. What number, if you cube it, will be 0? What cubed is 0? 0, right? 0 cubed, which means 0 is also a 0 of the numerator, which means this takes away that vertical asymptote. So even though it was a 0 of the denominator, since it also is a 0 of the numerator, it means it's not a vertical asymptote. So your only vertical asymptotes are x equals 10/3 and x equals -3. So that is the vertical asymptote part of this lesson. Now we're going to talk about the horizontal asymptotes. And they kind of have a chart that you look at to determine where the horizontal asymptote is. And again, a horizontal asymptote is kind of like a vertical one. It's just going to be horizontal. Horizontal asymptotes have to do with the degree of the numerator and the denominator and how they relate to each other. If the degree of the numerator is, what am I going to do first? Less than the degree of the denominator. Okay? So what would that look like? That would look like if your function, so if the degree of the numerator was x squared and the degree of the denominator is x cubed. So it would look something like this. So this degree is less than this degree. If that is the case, that means your horizontal asymptote is y equals 0. So there's 3 different options, right? Because what are your 3 different options going to be? If the degree of the numerator is less than the degree of the denominator, vice versa. If the degree of the numerator is greater than the degree of the denominator, or the last possibility is if they equaled each other. So let's look at those 3 different options. Okay, I'm not going to write out all these words. So degree of the numerator, this time instead of less than, I'm going to do greater than the degree of the denominator. So what would that look like? That would look like if your function was something like this. Where the numerator had the higher degree. So again, degree of the numerator is greater than the degree of the denominator. That means there is no horizontal asymptote. There just isn't a horizontal asymptote in that situation. And the last option is if the degree of the numerator equaled the degree of the denominator. So that means they would be the same, for instance, like this. The same degree. So since these have the same degree, your horizontal asymptote is at y equals the leading coefficient of the numerator over the leading coefficient of the denominator. In other words, this right here. Y equals, again, this leading coefficient over this leading coefficient. So this, if it was this problem, it would be y equals 3/7. So again, 3 options. The degree of the numerator is either less than the degree of the denominator, like this one, which means it's automatically at y equals 0. If the degree of the numerator is greater than the degree of the denominator, like this one, there is no horizontal asymptote. Or if the degrees equal each other, for instance, they're both squares, your horizontal asymptote is going to be y equals whatever the leading coefficients are. The top leading coefficient over the bottom leading coefficient. So let's look at some of these. So the horizontal asymptote problems start at number 11. Where you have f of x equals 2x squared plus 5 over 5x squared minus 4. So again, it's asking you to find the horizontal asymptote. So you want to look at the degree of the top compared to the degree of the bottom. Well, the degrees of both of them are 2, right? They're both x squareds, which means their degrees are equal to each other. So if you went back to that chart, your horizontal asymptote, when the degrees are equal to each other, are y equals whatever your leading coefficients are, the top over the bottom, which means this one will be y equals 2/5. Number 12. F of x equals x squared minus 7 over 6x to the 4th plus 7. So determine the horizontal asymptote. So let's see, the degree of the top is 2. The degree of the bottom is 4, which means the degree of the numerator is less than the degree of the denominator. That was that first way that we had written on the board. If the top was less than the bottom, your horizontal asymptote was automatically y equals 0. And number 13, this will be the last one that we do today. F of x equals x to the 3rd minus 4x squared plus x minus 5 over x squared minus 20 so the degree of the numerator is 3, the degree of the denominator is 2, which means the degree of the top is greater than the degree of the bottom, and when that occurs, that means there is no horizontal asymptote. Okay? All right, we will wrap up 8.5 on Wednesday. We'll do that one problem that we skipped, number 3, and then we'll do 14 through the end on Wednesday.